Case study, Enhancing Cybersecurity with AI, a case study on Technova's innovative solutions for network threat detection and mitigation. Detecting and mitigating cyber threats has become exceedingly complex, necessitating advanced solutions like artificial intelligence to maintain robust network security. In a metropolitan city, Technova, a medium-sized tech company specializing in artificial intelligence applications, faced a daunting cybersecurity challenge. Alan, the company's chief information security officer, was well regarded for his expertise, but was increasingly concerned about the sophistication of emerging cyber threats. One Friday afternoon, Alan received an alert that a significant volume of unusual network traffic was detected. Initially, the traditional intrusion detection system flagged it as unusual but could not identify the specific threat. Realizing the limitations of their current system, Alan decided it was time to enhance their network security with AI-driven models. Could AI truly offer a more dynamic defense mechanism compared to traditional methods? To address his concerns, Alan convened a meeting with his team, including Sophia, the lead data scientist, and Mark, the senior network engineer. They agreed to test various AI models to detect and respond to this anomaly. Sophia suggested starting with supervised machine learning models. She explained that by training the system on historical network traffic data, it could identify patterns indicative of known threats. Alan wondered about the model's effectiveness in countering novel threats. Would a supervised learning model suffice, or should they also explore unsupervised methods? Sophia highlighted that unsupervised learning models could detect anomalies without prior labeling, potentially identifying deviations from normal behavior that might indicate previously unseen threats. Mark raised a point about the propensity for false positives in unsupervised learning, emphasizing the need for fine-tuning to balance sensitivity and specificity. They agreed to use clustering algorithms to group network activities where deviations could flag potential threats for further investigation. Curious about deeper insights, Alan tasked Sophia with implementing deep learning models, particularly convolutional neural networks for malware detection and long short-term memory networks for analyzing patterns in network traffic over time. How would the team ensure these models generalize well to real-world data, considering the volume and variety of network traffic? Sophia explained that deep learning models require substantial data and computational resources for training. They decided to leverage their existing datasets and cloud computing resources to meet these demands. However, obtaining high-quality labeled data posed another challenge due to privacy concerns and the proprietary nature of network traffic data. Could federated learning offer a solution to this data privacy issue? Federated learning enables models to learn from decentralized data sources without sharing raw data, enhancing privacy while improving model robustness. Alan suggested collaborating with other firms to implement federated learning, ensuring compliance with data privacy regulations while benefiting from a diverse dataset. To further enhance their defense mechanisms, Mark proposed exploring reinforcement learning models that adaptively learn optimal strategies through trial and error. By continuously learning from network interactions, RL models could dynamically adjust detection policies based on performance feedback. Alan questioned the practicality of deploying RL models in a live network environment. How would the team manage the potential risks associated with the RL model's learning phase? They decided to initially test RL models in a controlled environment, simulating various attack scenarios to fine-tune the system before deployment. This approach would mitigate potential risks while ensuring the model adapts to real-world conditions. Sophia also brought up the challenge of model interpretability, especially for deep learning models often considered black boxes. Understanding AI model decisions is crucial for gaining trust and ensuring compliance with regulations. Techniques such as shape and lime were discussed to interpret model predictions, providing insights into the features influencing decisions. By enhancing transparency, these methods would make AI models more acceptable for deployment in network security. Over the next few weeks, the team implemented the AI models and began monitoring their performance. They observed that supervised learning models effectively detected known threats but struggled with zero-day attacks, underscoring the importance of using multiple AI techniques. Unsupervised models, on the other hand, flagged numerous anomalies, some of which were false positives requiring manual inspection. How should the team balance the trade-off between false positives and missed detections? Sophia and Mark fine-tuned the unsupervised models, adjusting thresholds to reduce false positives while maintaining sensitivity to genuine threats. They also integrated the deep learning models, which showed promising results in malware detection and network traffic analysis. The LSTM models in particular excelled at identifying patterns over time, proving invaluable in detecting sophisticated attacks. Leveraging reinforcement learning, the team noted improvements in the system's adaptability. The RL-based intrusion detection system adjusted its policies dynamically, enhancing accuracy over time. However, Allen remained cautious about the computational demands and resource allocation. How should Technova manage the computational resources required for AI model training? They explored cloud-based solutions and edge computing to distribute computational loads effectively, balancing on-premise and cloud resources to optimize costs and performance. Allen also emphasized the need for ongoing research and investment in AI capabilities to address current limitations and enhance future performance. The results were encouraging. AI-powered systems reduced the average response time to detect and contain threats, significantly minimizing potential damage. Automation of routine tasks allowed the security team to focus on complex issues, addressing the shortage of skilled cybersecurity professionals. The proactive threat hunting enabled by AI detected indicators of compromise that traditional systems often missed. Reflecting on the outcomes, Allen and Sophia considered the future trajectory of AI in network security. They identified promising areas for further research, including adversarial machine learning to enhance model resilience against deception attempts. By simulating adversarial attacks during training, AI models could learn to recognize and resist sophisticated adversaries, ensuring continuous protection. The integration of theoretical AI models into Technova's network security demonstrated their potential in providing dynamic and adaptive defenses. Machine learning, deep learning, and reinforcement learning each contributed unique strengths, from detecting known intrusions to identifying novel threats and adapting to evolving environments. Despite challenges related to data quality, computational demands, and model interpretability, the benefits of AI in network security were undeniable. In conclusion, Allen's team successfully demonstrated the practical application of AI models in enhancing network security, paving the way for more resilient solutions. By addressing each challenge methodically and leveraging cutting-edge AI techniques, they fortified Technova's defenses against ever-evolving cyber threats. The continuous research and development in AI promise further advancements, ensuring robust and adaptive security in an increasingly digital world.